Hello everyone. I'm your instructor, Devavrat Shah. I'm going to talk about multidimensional data. We'll start by discussing what multidimensional data is. From there, we'll start thinking about visualizing it. As we want to visualize, especially visualizing 10-dimensional, 100-dimensional, million-dimensional data. As a human, the best I know is 3-dimensional data to visualize. So how do we think about that? That's where we'll introduce notion of principal components that will help us think about visualizing very high-dimensional data. The method to find principal components is what's called principal component analysis. So we'll describe that briefly. We'll discuss various perspectives in terms of what principal component analysis is trying to do. And finally, we'll think of principal component analysis as a simple generative mechanism with an example of images of cats. We'll try to see how principal component analysis can provide us a generator, a cat image generator from multiple cats. In a sense, that's a simplistic way to think about different types of modern AI models, whether they're called diffusion models or generative models like language models. From this, which is just understanding of data, we will go to estimation question, and how do we estimate parameters associated with multidimensional data. Talk about key estimation procedure, plugin, feature matching, maximum likelihood estimation or ML. And finally, as we think about multidimensional data, multiple parameters, when we have too many choices, we want to figure out how do we make a selection in a thoughtful manner, also called model selection. We'll discuss the notion of model selection, and then we'll discuss one criteria called archaic information criteria, or AIC for short. It's one criteria. We will discuss it as an example to solve a generic problem. Don't take that one criteria as the best way to do everything, but just an example. But it allows us to think about what is model selection and how does one go about doing it. Multidimensional data. In the simplest form, one wants to think about multidimensional data as a collection of things, a tuple of things. For example, data about an individual, their height, their gender, their weight. And we have data about many different people. If you want to visualize data like this, one way to do that is to say, well, first I'm going to just understand what people's height looks like. Take a one at a time. Or you might say, well, I'm going to look at people's height and weight together. Two things at a time. Remember, we have a third thing, gender. How do I do that? Well, maybe I want to pull something out of my screen. Or in this case, it's gender, and let's say gender is 2 or 3 or few things. I can color each data point by that. And that might help. But what if there's a fourth dimension? Okay. Or what if there are 500,000 dimensions? So here I'm just showing you a caricature of a type of data set that we might discuss later, is where I've got 3,000 individuals. These are individuals who have origins from Europe. And we have for each one of them 500,000 DNA sites. And visually it might look something like this, messy. How do we visualize that? Now that's a challenge. Even if we make it simpler, here's another example. So this example data set is about marketing campaigns. Each row corresponds to one campaign. Numbers here talk about how much money, normalized sense, we spent on TV marketing, radio marketing, newspaper marketing, that leading to normalized sales. Okay. And now we want to understand this relationship between TV, radio, newspaper sales, because we believe that they're driven by each other. If we want to do two things at a time, we'll do something like this. That is spending in TV versus sales, spending in radio versus sales, and so on. And as we can see, at least visually, maybe these are capturing trends, but these are capturing trends that are simply relative to two things, not relative to all four things. Or if there were 500,000 things, not relative to all 500,000 things. So in a sense, we want to capture key trends in the data while keeping all the things in mind. Okay? If we can do that, then maybe we are able to start visualizing certain things. And that's what we want to go towards. With aim of identifying key trends in the data when data is multidimensional, very large dimension, we want to capture a notion of principal components, and that's what we're going to discuss next. So again, imagine you have n data points in p dimension. Think of p 500,000 and 3,000. And now we want to understand what are the key trends. Here visually I'm showing that there's a data in 2 dimension. These are all different data points. Okay? But there is this one trend that is truly capturing the essence of it. How do I capture that trend? More generally, maybe in a simplistic mental model, just so that we can think about and discuss about, maybe my data is in n dimension or p dimension here, but it's all just multiple of one principal component or one component. If we were to think of data in a table form, for example, I might have a big spreadsheet with different rows, and let's say there is one row, okay, and one row has value 1 to 100. Let's suppose this row is 2, 4, 200. The row above is -1, -2, -100, etc., etc. But this seems to suggest that this row is 2 times this one. This one is -1 times this one. So if I forget about this row, really, these rows look like data like this. So this is my 0. The bottom row is 2. The other row is -1, and so on. So in a sense, now I have found a one-dimensional representation of this very, very high-dimensional data. How do I find this? That's what is principal component. And we're going to look for that. We're going to look for that even when data does not exactly look like this, which is what reality would be. Data is more going to look like this, as in perturbation, approximation around principal component. Now, let's take this simple example setting to define how we will go about looking for it, and then we can sort of from there come up with a generic method. So with that setting in mind, what we are really looking for is a direction V so that they're most aligned across all data points. Okay? The reason that is the case is because if we think of setting where xi equals to alpha I u for every I, then xi transpose u is this, or more generally, xi transpose v equals to alpha I u transpose v, and this one is maximized when u equals to v, especially when u is unit norm. And that's what sort of will give us this coordinate too. So really, we are trying to maximize a component like this over choices of v. Let's sort of look at this a little bit more carefully. Okay. So this is what we are trying to maximize. Well, I can write this as xi times v and xi times v, which is what I have done here. But then we can sort of swap these things. There's v transpose xi and keep this as is. then we can club these two things like this and keep these things outside. But I has nothing to do with the V, so we can take this I inside, bring the V's outside, and now we are left with this term. Okay. What this says is that each of my data row, so this was my xi transpose, and this is my xi. Okay. And these two things multiply to produce a matrix, which is what this is, and then we are adding up those matrices. Okay. In summary, one way to find our principal component is to maximize this term, where S is this data matrix as it's called. Typically, you would normalize it, and they're trying to maximize V transpose SV. Okay. Solving this problem would lead to identifying your principal component. If you try to look for first V1 that maximizes, then V2 that maximizes, V3, then those will be next set of components. The largest component is actually what people call singular vector of matrix S. S in this case is a symmetric matrix, so it's also called eigenvector. Okay. And multiplication of X with V for each data point gives you the coordinate. So in a nutshell, after we find the best V, xi transpose V, you call it coordinate alpha I, and you're approximating xi with alpha I times V as representation. Okay. Typically, when one does this kind of data analysis, you try to normalize the data by removing the mean and so on. But those are just pre-processing steps. Okay. So this, in a nutshell, is a way to find your principal component. Okay. Now, this is the material for advanced setting. Here we are trying to explain why maximizing V transpose SV corresponds to identifying the largest singular vector, or in this case, largest eigenvector. So S, the way it's represented, is a data matrix, which is a symmetric matrix. Because it's a symmetric matrix, it has nice singular value decomposition. It's a nice symmetric in the sense that is each left and right singular vectors are equal. You've got eigenvectors or eigenvalues in this case, which are sorted. And then when we apply V transpose SV, since each one of these U1, U2, UP are orthogonal to each other and normalized, effectively, this would be nicely decomposed into this form. And as this happens, the term that maximizes this quantity is the one which has the largest lambda I. And therefore, V equals to U1 is the best choice that you would get, which will maximize the answer, which will lead to the lambda max as the answer or as the value or a solution of this optimization. From this, it also suggests that the next component that you want to look for is the second eigenvector. After that, third, and so on. If you go to K, it's a kth eigenvector. This is ending the advanced part. Now I'm going to summarize the algorithm. So in summary, the principal component analysis identifies principal components from multidimensional data as follows. You have data x1, x2, xn. Each one is p-dimensional data. That is, you have a spreadsheet with n rows and p columns. First, you form this normalized data matrix by subtracting mean from each row and then computing this quantity. You compute k singular vectors of this matrix S, gives you V1, V2, Vk. For each data point I, you compute these as your coordinates. And these coordinates, along with direction V1, V2, Vk, give you k-dimensional representation. We will talk about few perspective on principal component analysis, or PCA. One way to look at what PCA is trying to do is it's trying to find a line, a plane, or a lower dimensional surface so that when you bring your observed data towards that, you have minimized the error. Putting it another way, you maximized what you have preserved from the data, maximize the variation in data. And visually, that's what this is trying to explain. So one of the reasons why PCA is also thought as projecting into a lower dimensional surface, which preserves most information in the data. If you are thinking from a generative model, a probabilistic perspective, what PCA suggests is that, well, you have data that you're observing that are coming from some underlying jointly Gaussian distribution. There's some notion of a mean and some notion of a covariance matrix. And what PCA is trying to do is trying to approximate each of the observation by retaining only the top aspects or top components of your covariance. And that primarily follows from a Gaussian perspective where your data, one way to think about data generated as this, is the mean plus independent Gaussian z's multiplied by vectors vk, where vk are eigenvectors of your covariance matrix. Okay. And PCA primarily tries to remove everything after, let's say, D when you're doing D-dimensional PCA. Okay. So putting it another way, data is generated as per some high-dimensional structure, and you're trying to find the meaningful top D-dimensional structure that exists in data. And that's what PCA is implicitly does. Here is a nice example of applying PCA to a data set that is reported in this work, Genes Mirror Geography within Europe. So what was the data set? Data set 3,000 individuals, think of 3,000 rows, and 500,000 columns. Okay, each individual row corresponds to genotype information of an individual originating from Europe. Okay, for this data set, we apply PCA with 2 dimensions. So each individual now gets effectively 2 coordinates. Let's call it x coordinate, y coordinate, individual 1, 2, up to 3,000. Okay, and based on that, we plot them on this xy axis. So this is PCA1, so let's call this x and this called y. Okay, and then you plot an individual here. After you plot an individual here, you say, okay, let me go back to that individual and understand which country they come from. And let's say they come from the country, which is in this case DE. Okay, it has a color yellow, so I'm going to sort of color that point with the yellow. Okay, somebody comes from Switzerland, I'm going to color them with pink, and so on. So that's what we have done coloring here. And now you look at this and you rotate your head a little and then compare it with this, and you start seeing that, visually it's capturing the same geography that you have on this map. In that sense, genes are mirroring geography. When you see this, you feel good about it because it seems like by applying a method that has no idea where people are coming from, by simply applying it to very high dimensional data, you're able to capture this structure. So now you have a confidence in it. And now you can do something meaningful with this lower dimensional data because you feel it has captured the right information downstream. And that's one of the purposes. We're going to discuss how PCA can be thought as build a generative model for images. That is, you will give me number of images, I will apply PCA, and that will help me build a model so that if you come and tell me that generate a new image that looks like a collection of images that you've given me, I can do that. This is a way to explain what is happening behind the scene, but in a much more complicated manner in modern generative model, modern generative AI. So here is a setup. So I've got images of 1,000 cats. These are just some examples of those images. If you're a cat lover, you would love them. If you're not, still they're nice. Each of this image is grayscaled. That means, and it is 64 by 64. That is, there are 64 rows, 64 column, and each one of these are pixel. So effectively, there are 4,096 total pixels. What we'll do is we'll flatten them and make them vectors. So for example, this image, let's say all the pixels here will become first set of 64. Next set of pixels here become next set of 64, and so on. So I've got 64 such blocks, 64 times, okay? And when we have that, what happens is the total length here is 4096. So effectively, each image became a vector of length 4096. And I've got 1,000 such images. So now I've got this multi-dimensional data with 1,000 rows, 4,096 columns. And now I'm going to apply PCA. Okay. As you do PCA, you want to choose how many dimensions to preserve. Should you do PCA with 1, PCA with 2, PCA with K? Typically, there is a nice way to look at it, and what people call this is the spectral plot of your data. In particular here, we took that data matrix associated with this 1,000 cats of 4,096 dimension, and we are plotting their squared singular values. And what this shows is that initially our first few are very large, but soon they're becoming small. So in a sense, we really need very few components to preserve most of the energy. And that's how most auto aspect of PCA decide. Okay, so let's say you made that decision. In this case, we would make the decision that we're going to preserve 8 top components. So this is my mean of average of cats. So I had vectors of those cats. I compute average of all those vectors. Then I flip them back to this image form, and that's what this looks like. I found K principal component, in this case, K equals to 8. This is how the first principal component looks like. This is our second, and so on. And that's what I would call my eigencats, the principal cats. And I will keep them on the side. Okay, so I've got 9 cat images or 9 vectors, and I will keep them on the side. These are very important because now you give me any image in cat image in my data set. Effectively, I can write that as my mean cat plus some coefficient times first vector plus some coefficient times second vector, and so on. So in a sense, now what has happened is I've got effectively all of these cats, if I've had K equals to 8 dimension, I'm going to represent this as if it's 2 dimensions so that I can present. But each cat now looks like a number or a point in 2 dimension, or more generally 8 dimension. Okay. So now I've got this empirical distribution over cats, which is 2 dimensional. Actually, in this image, in this my illustration, but actually 8. Well, once I have this kind of empirical distribution, let's call it p hat over 8 dimension in this case, I can fit some parametric model on it. Let's say a multidimensional Gaussian or your favorite model. Okay. So let's say from this, I learn some parameter associated with that parametric model. Once I have got this parametric distribution, I can sample data point from this. And let's say I've got sample data point 0.1, 0.2, let's say 0.4, dot, dot, dot. Whatever these data points are, I can take this and then say my new image, my new randomly generated image, new image equals to my mean cat, which is like this, plus 0.1 times my this first icon cat, plus 0.2 times my second icon cat, and so on. This gives me a new vector or a new cat image. And that's my random generation, and that should look like the distribution of original cats. So in a sense, now we have a very clean way to generate a new image that looks like existing cat images. No voodoo, no complicated stuff. It's all in front of us. Now, of course, if you want very, very nice, sharp images, you want to actually prompt them, you want to constrain them, you need a little bit more structure around these things rather than just this simple structure. However, this is the essence of all this modern technology. Let's discuss estimators for multidimensional data. Okay. Let's start with 2-dimensional data. In 2-dimensional data, we have a distribution over 2 things, whether it's a discrete distribution or continuous distribution. We sample data from this distribution. In simplest model, these are independent samples from this distribution. Visually, they might look like this. And from this, we want to build an empirical distribution over 2 dimension. When we think of empirical distribution over 2 dimension, really for any area in 2 dimension, we want to understand what fraction of data points fell into it. For example, in this triangle, where true underlying distribution has probability half, we observe that 4 data points have fallen into that, and hence empirical distribution is 4 over 10. Okay. Now, once we understand this notion of empirical distribution, that is, effectively each data point is getting, as before, 1 over n probability mass, which is same as before, just visually things look different. All estimation procedures, whether it's a 1 dimension or many dimension, remain roughly the same. For example, if you want to do plug-in, so if you want to estimate expectation of some function of our 2-dimensional data set, we'll simply replace actual expectation by empirical, which is putting 1 over n mass on each of the data point xi, yi, applying function to that and computing the average. This can help us compute things like covariance in this form. Okay. You can think of any other complicated property and it would be the very same structure. That's our plug-in estimator. Again, nothing new. It's the same thing applied, just looks a little bit more complicated. Let's think about feature matching. Likely in multidimensional data, our parameters are multidimensional, and we might have multiple features associated with data. For example, let's suppose that I have a distribution with there are 3 parameters, and the features of my interest is individual mean and then their mean of their product. So I will compute this from empirical data. Then among all choices of theta, I will try to find theta so that this is satisfied as well as possible. And that will lead to matching my feature to my empirical data. Again, nothing new, same as before. It's just instead of one feature and one empirical moment, we might be doing for multiple things. Maximum likelihood, same story, just like single variable. Okay. We're trying to look for parameter, which may be multidimensional. We are observing data, which is multidimensional. We compute the likelihood under different choices of parameters, and over all different choices of parameters, we try to find the one that maximizes it. In a sense, whether estimators are plug-in, feature matching, or a maximum likelihood, approach remains the same. Things got a little bit more complicated because of multidimension. Very similar properties that hold analytic, central limit theorem. We can think about bootstrap. We can use that approaches to compute sampling distribution, produce properties of estimators, and then also talk about confidence interval. One thing to remember, confidence interval typically are defined for one thing at a time, and so that's what we have to do. But other than that, nothing new. And that's a good thing. Let's talk about model selection. Here we are trying to think about different choices of models that we have, given data, try to decide which model is better. And things get a little complicated when we think about better. And that's why we want to discuss in detail what model selection means and how do we go about it. A good example to remember is Weldon's Krebs data. Weldon, as we know, along with Mrs. Weldon, went to Naples in 1890s to collect data about crabs. Effectively, they were capturing crabs on the beach, working hard for thousands of them, and for each crab they measured the height is to width ratio, a number. And they were trying to understand in a data-driven manner whether the hypotheses at that time that were put out by different life scientists or biologists at that time, whether attributes of every species and the normalized attributes of every species is Gaussian or not. And what they concluded effectively with the help of Pearson, that the data that they had collected, which visually looked something like this, was a mixture of two Gaussian. Okay? What that meant is that, yes, the hypothesis that they were trying to verify was not really false, but in a sense it was a little bit nuanced. That is, crabs, the ones that they collected, came from two different related species, and for each one of the species there was a Gaussian distribution. Now at this stage, Mr. and Mrs. Weldon along with Pearson could have asked the question, why just stop at 2? Why not fit, let's say, 3 Gaussian that also leads to same thing? Because if 2 fits, 3 fits too, and then 4 fit too, and 5 too. So why not go to 5 and stop there? And why 2? It was clear that 1 did not fit, so 1 had to go beyond 1. But why stop at 2? This is where question of model selection comes into play. Okay? And so what we're going to do is we're going to sort of first discuss philosophically and then take a simple example to discuss that. Philosophically, you want to stop when things are explained in a simplest possible manner, because if they're explained in a simplest possible manner, then they will extend generalized well as well. As for unknown, unseen things, they would have most affinity. That's the belief. Okay? In going back to Weldon's example, Mixture of two things explain things well, mixture of one did not. Mixture of three also can explain, but two is a lot simpler, and hence maybe we should stop. How do we formalize this? And this is, to formalize these things, we need criterias. Here we'll discuss one of such criterias. Again, there are many criterias, but this is one of the criterias to ground our discussion a little bit in this philosophy. This is called archaic criteria. What it tries to do is it tries to choose a model that is higher likelihood for unknown things. I generalize as well. Now, to formalize this criteria, archaic in 1970s came up with this really interesting observation. The observation said that for large class of setting, when we are doing maximum likelihood estimation, the logarithm of likelihood of new data under your estimator based on old data, on average, behaves like what you would see empirically for the data that on which you have fit your estimator, plus or rather correction in terms of model complexity. Okay. So this is kind of interesting because what it says is that let's assume that you have observed n data points. Based on the n data points, you produced an estimator. Using that estimator, you can compute this empirical log likelihood. This is a very good proxy of what would happen under likelihood for a new unobserved data coming, which is following the same distribution. Okay. But that likelihood, which is of our interest, we want to have that as large as possible because that's what is a good faith, good generalization. That is reduced by empirical minus model complexity, where P, in a sense, is how complex your model is, and N is, of course, number of data points. And now this can be very, very useful for us to break ties, right? Because imagine that I've got two models. One I will call model class theta, another I will call model class tau. Weldon's example, mixture of two Gaussians, mixture of three Gaussians. Okay? So let's say, first we think of mixture of two Gaussians or model class theta. We learn the best parameter. We compute this empirical likelihood of all the data points we have observed, minus the dimension of this. Again, if it was mixture of two, this would be 2. We do the same thing for other model class and then reduce the dimension. Let's say this was 3. So we will choose this one over this if it's greater, because of course it generalizes well. What this suggests is that when we increase model complexity by 1, for example, it better be that this empirical thing is increasing compared to the previous one by 1 over n. Because if not, you will sort of go in the favor of a smaller model class. For Weldon setting, that's exactly what happens, and hence you stop at 2, effectively. Let's apply this criteria and see it in practice how it looks like. I'll take a very simple example, but it will be fun to look at it. Okay. So what we're going to do is we're going to take daily temperature, so daily average temperature for Seattle from 1947 to 2017. This is roughly 60 years of data. If you think of 60 years times 70 years. 70 years times 365. That's a lot of data points. Okay, take it. So think of 400. Then we are looking at roughly 28,000 data points. So lots of data points. A simplest model is these data points are generated from one Gaussian with mean mu and variance sigma square. A little bit more evolved version would be where for each day of the week, that's a separate thing, and then everything in between. So 2-parameter model, 4-parameter model, 6-parameter, 14-parameter. Let's fit it to data. Well, if we fit it to data, as one would expect, more the number of parameters, better training fit it is. So that's what this chart is showing. Effectively, on x-axis, I have number of parameters in model. On y-axis, I have what's called negative log likelihood. So you want higher log likelihood, which means smaller negative log likelihood. So that means this is good. Okay. And of course, more parameters you have, you will have better fit. But then you can ask question, is that what a cake criteria would suggest? So you can do correction to this. And when you do correction to it, actually it goes in the opposite direction. With correction, things get worse. And so this is where you ask question, is this the right thing our criteria is doing? Well, let's think. So Seattle, like many other places, have seasonality, which means that temperatures have patterns that are related to months, not days of the week. And when you try to fit days of the week in summer and winter all together, you are going to create a mess. And hence, maybe this is worse than just two parameters. But then if we truly believe that it's that issue, let's bring some form of seasonality modeling, i.e., let's now introduce separate parameters for each month. Months capture seasonality. And then let's go through the same exercise. And we go through the same exercise and voila, as we expect, even with AIC correction, it follows the same trend. That is, more complicated the model is, better it is a fit. So indeed, simple example, but gives us an idea how to think about model selection. A criteria like a cake is one way to do it. There are many other ways to do it. But hopefully this gives us to think about philosophically, concretely, how to go about model selection.